Well, here we are again for the fourth of my LED lamp teardown videos. I had hoped to come onto this one last time, but we ran out of time. I gave you a little hint of what was inside and that it was going to be actually rather interesting. I remember now that this was actually the first, I'm fairly sure it was the first LED lamp that I ever bought, and it must have been practically 10 years ago now. I can't quite date it exactly, but I remember the project that I was working on in London at the time, and in London I came across a small chain of lighting shops. Can't remember the name. It'll probably come back to me. If it does, I'll mention it at the end. And they at the time were doing these very early LED replacement lamps, and I think they were doing a special offer on them, so I got one or two. So it's actually lasted better than I thought. Might well have been in the on the landing for 5 or 6, 7 years even, but it did eventually fail. It should have lasted longer than that, but it hasn't done badly actually. It took me a little while to get inside this, and in fact the teardown I did as a series of little clips which we'll run into straight away. So next I looked at this other bayonet cap conventional style LED lamp. Now this seemed to have a glass envelope, so I couldn't just cut it open. It wasn't at all clear actually what the construction was, because you've got a lot of metal here, and you've got some metal inside, some vent holes as I remarked before, so it looks a good construction, but how to get into it? I thought about this for a little while. There's a little gap down there, and I tried prying there, and in fact the glass actually moved a little bit. I thought maybe if I just applied the pressure and maintained it, the glue might just gradually give, but it didn't seem to. So the other way to get glue to release is with a hot air gun. So I tried some of that, aiming that around the base, and tried aiming it up in the little vent holes as well there, and then tried lifting. I'm not sure whether that was having very much of effect, but I tried just maintaining the pressure like that, and all of a sudden there was a pop and the whole thing smashed and fell off. That left various bits of shards of glass around there, and in fact with the hot air blower on there, this sealant released those remaining shards of glass, so I was able to get rid of those. Then inside, this is quite interesting. We've got these 4 LED packages, and we've got 2 extra little chips there. Now I'm somewhat puzzled. I'm still wondering what those do. Let me bring it up close. If I expand that as far as it'll go. And there, each of those little LED chips, each of those little copper-coloured kit chips seems to have 2 wires in it. Now, whether my first thought was those are 2 extra LED chips, perhaps to balance the colour or something. And the whole assembly has just got these 2 wires going to it, and there's some sort of sealant sealing it down to there. These LED chips in here, there are probably a couple of LED dye in each of those, and they're covered basically. The way the white LEDs work is that you've got a blue LED and this fluorescent coating on top of it, which adds the remaining colours of the rainbow. So I wondered whether those 2 were in order to balance up the colour or something. That's rather unusual, because if they were just, I don't know, a control circuit, then why give them a transparent blob on top? Very strange. So also looking at this, we can see the construction a little better. My first thought was to look in there, see whether I could see in there how it was built. And by shining the torch from my smartphone in there, I could see in there just a little bit better. And I couldn't see what we can see quite easily here now is those little fingers. And they've got two metallic shells here. The inner one, we've got a very good heat sink here, which is attached to the inner metallic shell. And we've got these fingers which help, well, probably they only just retain it in the outer one, so there's plenty of room for the air to circulate between the inner and the outer. So this is actually quite an impressive design. Nevertheless, it did fail quite quickly. Now at this stage it would be nice to test those LED chips and see what I could find out about that. But if I were to peel any of this off, they're going to be very fine. You can see there just how fine the bond wires are from that chip onto the circuit board, and they certainly wouldn't survive taking the that off. So I think the next thing we'll have to do is undo these screws and take this off and see what sort of circuit we've got underneath. Okay, I'm going to have to pause that because I haven't done that yet, and we'll come back shortly and see what we can find inside, and hopefully from the circuit inside we might be able to surmise what those chips are actually doing. Okay, so I cut away the silicone around these screws and took out the screws. Then nothing seemed to move very much. I tried easing this, and it turned out I was afraid that these tabs might actually be spot welded to the surround, but they're not. But just lifting it a bit, it did actually move, but it doesn't seem to want to come right out at all. But then I just noticed that in fact there's a gap appeared there, so maybe if we cut away this rim here we might be able to take that off that way and get to the next level. Okay, the only other thing that I've spotted was that inside here there was a poor little dead ladybird. Okay, so that obviously crept in there at some stage and was enjoying the warmth, but it got too much for it. Okay, so that definitely wasn't a cause of the problem, but it was interesting to see that having these vents in there also means that it can be a nice little place for insects to get in. Okay, so I'm going to have to cut this away and see what I can do. Let's try that. I'll pause this again and come back when I've got something more to show. So trying to cut this down here and leaving it up there didn't seem to be doing anything very much. But when I put a screwdriver in this crack and levered it up, it gradually lifted a little bit. When I forced it, it actually popped. And in fact, what happened is that the two leads there broke. I could then lift this straight off. And in here, there we have the works somehow completely encased. Well, I hope this isn't going to be another case of the innards being totally encased in gunge. So I'm going to have to see what I can do with that. So just before I go and attack this, actually, well, my first thought was to use the Dremel cutting disc to cut around there. But in fact, the cutting disc was very good on metal, but on plastic, basically just melts it. Has the same effect eventually, but it's not so clean. So I might just use the hacksaw, which is what I used on that previous one. But before I do that, interesting construction here. That actually comes out there. We've got some heat sink paste in order to get the heat from this inner to the outer, and this seems to be bonded onto the top there. So if you can see in there, this is just sort of a dome. This bit, okay, that's just comes off there. And again, we've got some heatsink paste getting the heat from there to there. And there's plenty of heat sinking here, so long as it can get from this little thing onto the base, and that might be the limitation. Right, off to find the hacksaw. So here we are. I took the hacksaw to this plastic piece and sawed all the way around there, and this then came off quite nicely, leaving the control board in there. It was still difficult to get this out, so I thought I'd try cutting the base and getting the base off. The other thing I tried was on the base we've got these solder pads which connect with the socket that it's plugged into. I thought I could maybe just unsolder those or melt that solder and pull this out, but that didn't seem to work. Actually, before I even did that, I thought to myself, these solder pads very often are a fairly high temperature solder, certainly lead-free solder, which can be quite difficult to melt. So I tried the Dremel cutting wheel on that, but that didn't work at all. It just sort of melted a little groove in it. But that said, I came back. Well, while I was down there in the garage with the Dremel, I cut this open here and here, so that I could open it there, and that allowed me to get inside. You see it's the little dimples there where it's pressed in, so it takes a little bit of force to open. Another thing to notice is this base is actually glass. If you look close, you come in close. Is that going to focus? Doesn't seem to want to. What's the matter with it? There it is. And if you look very carefully, you might be able to see that even though the cutting wheel has gone right through and made a slight groove in the glass, the metal still goes across. So the metal is actually embedded into the glass slightly. So presumably these bases are made, the metal is pressed into the right shape, and then the glass, the hot glass, is then fitted into here with the and it basically expands into the base to make a very secure fitting between the glass and the base. Anyway, I opened it. We're back in focus on the desk. There we are. Okay, so I opened it. When I got inside, I found, in fact, I did actually manage to open this, but in fact I could then pull this off here, and there's actually enough spare wire that I could have actually pulled that off, hopefully. But it was, whether it was round here, I didn't want to pull this too hard, but had I pulled it rather harder, it probably would have come out to something like that. So I could have unsoldered that, or at least got this sufficiently far out to disconnect and examine. Okay, so this is an interesting little board. Much more complicated than any of the ones that we've seen before. Let's take a look at it. Once again, let's bring it up close, and then you can see it properly. Right, let's focus in on that. There we are. Okay, so it's got that transformer. It's quite a big transformer, comparatively speaking. On that side, I turn it round so we've got the light on it. You can see that there are 3 connections going into a winding on here. Doesn't look as though there's one onto there, so that would probably be a centre tapped winding or something like that. And on the other side, it looks like we've got 2 separate windings there. So that's a relatively complicated transformer. What else have we got? If you look carefully, here's another interesting thing. We haven't just got one of these bridge rectifiers. It looks as though we've actually got two. One there and one there. They're identical. And that seems to be the AC input to both of them. So that produces DC there, and that produces another DC there. Well, this is actually a dimmable light. So I wonder whether the reason for having that is so that it can detect the actual phase of the AC mains coming in. Because, let me explain, if you have one of these feeding straight into a reservoir capacitor there, that will smooth out the AC turned into DC, with the result that you've got relatively smooth DC on here. Now, what a dimmer switch does, it simply contains a triac, which is an AC switch, and that basically, every time the voltage is continually going up and down, reversing and reversing like that. Every time it crosses zero, the triac switches off and then only switches on somewhat later during the cycle, with the result that less power actually goes to the load. Now, if you've just got a filament lamp, that works very well. You've just got less power going in. But if you've got one of these little rectifiers going into a reservoir capacitor, if the reservoir capacitor has got enough capacity, then it may be that can actually supply the current, even though we're only getting pulses from here instead of the normal full half waves, in which case the dimmer switch is not actually going to do an awful lot. So that may be actually detecting the zero crossings and detecting when the power comes on again a little bit later. In most of these we've got a little controller chip. Now all we've got here, we've got a little 3-pin, couple of 3. These are simply transistors, I think. And that, if you look very carefully, it's got a number which says, if I can get the light on it and the focus. Don't know whether you can see that. I think the writing's maybe the other way up. Let's try. .358 it says. Well, the 358, originally came out, I think, as the LM358. That's a very venerable chip. It's basically a pair of operational amplifiers in a single package. I'll come back to that in just a moment. And what else have we got? If you look underneath there, under the transformer, you can just see another chip there. Not sure what that is. And behind it, there's another 8-pin chip similar to that. You can just see it through here. There it is, between those two legs. I imagine that may well be another 358, but it's going to be a little bit difficult to get into that. Okay, so I was going to explain about an operational amplifier. Right, an operational amplifier, one of these 358s. Chips like that came out way back in about the 1970s. All it consists of, each is basically got two of these operational amplifiers. We normally could just call them op-amps. It's basically just a very high gain amplifier, so that whatever input you give it, it gives maybe, I don't know, perhaps 50,000 times the output. Well, provided that's not more than supply voltage. Obviously it can't provide more than the supply voltage, which means that you're probably only going to have microvolts on the input. One extra thing it's got two inputs. It's got a positive and a negative input. I think I've got the, here we are. Right, I'll put this on the screen. I've got the data sheet here. Okay, the 358, the different variants, you can have ones with 2 or 4 op-amps in a single package. Let's have a look. wide supply voltage range, 3 to 32 volts. Now does it give the actual gain? Don't actually see that if I scroll down a little bit. I'm scrolling down. You won't see this on the screen unless I put it up. No, I can't actually see where it says the gain, but typically the gain at DC might be something like 50,000 or something like that. Now we have got actually two inputs. Now here we've got a drawing of the package, and we've got inverting input and non-inverting input and an output, and the same inverting, non-inverting and output on the other side. So we've got two of these. Now what it amplifies is not the input as such, it amplifies the difference between the positive and the negative. So if you put negative feedback around this, it will tend to, if you connect the output back to the negative input, perhaps through some sort of network, it will try to keep the output such that the negative input follows the positive input. So if you just connect the output A to input A, then the output will try and follow the non-inverting input, because if the output changes a little, the change will be inverted and fed back to the negative input. So whatever change you put on the positive input will be followed by the output. So that's a simple voltage follower. And if you change whatever you put on the feedback between the output and the negative input, or there are various different games you can play to do all sorts of things with operational amplifiers. So it is an incredibly powerful and useful building block, which is used all over the place. Okay, so that's the op-amp, and we've got perhaps a couple of those. Now at this point, the first thing I'd like to do is to get this little transformer off and see if we can see whether that's another 358 underneath. Now for this I'm going to get my here's my solder sucker, and we'll see if we can suck the solder out of here. Let me get a bin as well. Right, I've now got a bin to put the solder in. Now I need my close-up glasses as well. Now, I don't know whether you can see this. I'll try and do it so that you can. So it's going to be a bit tricky. Let me start with that. So we've got 8 pins holding this little transformer in place. Now I press down the plunger, which loads the spring, and I have to melt the solder. It's jumping about a little bit. I don't know, I'm going to have to get my helping hand to this since you're not here to help me. So if that will hold it steady, it's a bit better. Okay. Melt the solder. Doesn't melt terribly easily because it's lead-free solder, and that sucked some of the solder off. The other thing you can do, a trick that's well worth knowing, is that if you've got lead-free solder and it's not melting terribly easily, the thing to do is to put some leaded solder on. And that mixes with a lead-free solder, and the mixture then has a much lower melting point. I'm going to add that to each of those 4 pins while I'm here. And that should allow me to suck the solder off much more easily. Then press the plunger down over the bin to get rid of the solder. Right, that one, that's got quite a lot of solder out of there. I can see a nice little hole there. Don't know whether I've still got this in view of the camera. I think I have just about. Move it over there a little bit. And one more. Now it's difficult to get the solder pump, the solder sucker, actually on top of the pin. Now that's not melting so easily, so I need to put some leaded solder on there. On each of these. And there's one there right up against that diode. It's going to be a little bit more tricky. Let me try one or two of those. There you see how the solder comes out when you press the plunger down. Okay, it's not coming out too well. That one, don't know whether you can see, but you can, there's a nice hole there around the pin. Not doing quite so well. And let's try this one. It's not bad. Okay, I'm going to pause at the moment because that's basically how you do it, and you continue doing that until you can just waggle the component on the other side, and eventually you can free the device. Let me show you a bit close up how this is going. There, so you can see on that one it's taken the solder out quite nicely, so you could probably press that pin a little bit and you could release it from the solder, which is sticking to one side of the hole. So it's just a question of persevering with this. So here we are. It's actually quite challenging getting this little transformer off because there are 4 pins either side, all of which have to be unsoldered. So actually getting the solder free was quite tricky, and in fact several of these pins actually came off as I was pulling the transformer out. Perhaps you can see I've pushed the pins back into the transformer. See if we can get it to focus again. You can see where the wire comes out of the transformer, and it's basically wound around the pin, and in lifting the transformer the pin stayed in the board and broke the wire. So if we wanted to test it, I'd actually have to unwind that wire from around that little post and remake the connection. While I was there, I thought I'd take out these little capacitors as well, because we can very easily test those and see whether there's a problem there. So bringing across my little component tester again, let's see what these say. 2.2 microfarads, 400 volts, 2.2, 400. So they're both identical. Now clipping these onto the leads, I can do this quite easily just by myself. Right, let's press the button, see what happens. Two 2174 nanofarads. Well, that's 2.1 microfarads, nearly 2.2 microfarads, and 14 ohms, which is quite a lot actually. But then there's a high voltage capacitor, and it's a low value one, so maybe that accounts for that. Let's try the other one and see whether that gives a... So the capacitance is fairly reasonable, but I'm not too happy about that resistance. Here we go. Right, 2.09 microfarads, that's 11 ohms. So there again, relatively high internal resistance. That may not be abnormal because it's a high voltage capacitor. So no great problems there. So coming back to this, I thought maybe that this little component here, when I was peering at it through the pins of the transformer, I thought it was another of these 358 operational amplifier chips. But no, it's actually something much more interesting than that. If we look very close, I was afraid it would be some fairly anonymous sort of Chinese chip, but no, not at all. So you're going to focus upside down. Not quite in focus. Right, so it's that symbol, the little icon there, is the Texas Instruments icon, which is encouraging because a very standard sort of chip by that reckoning, not just some anonymous Chinese thing. And the number is 2628600D. So we look that up on the internet and we find it is indeed a Texas Instruments chip. And I've got you can easily pull up the data sheet. It's actually a remarkably complicated chip. From the data sheet, this is an example application circuit. So immediately we can see, as we always do, where's my pencil to point, we've got the bridge rectifier coming in with the AC and a reservoir capacitor. Here we've got this little transformer, which is obviously this thing, and I noticed before we took it out that one of the windings, there were 3 connections, which is presumably those 3 there. 2 of those are connected together. And on the other side we've got a secondary. So how is this going to work? Well, I think we can only look at it very much in outline. So the heading on the datasheet is UCC 28600 8-pin quasi-resonant flyback green mode controller. Obviously this is much more sophisticated than any of the lamps that we've looked at previously. So once again we've got a transistor here, which is a switch, and the current obviously builds up through this coil, that part of the transformer through there, and this switches on and off. And when it switches off, we haven't in this case got a Schottky diode which takes it through an alternate path, but in fact whenever this switches off, since there's nowhere else for the magnetism to go, it basically dumps its energy into the secondary, and probably a little bit into there as well, and not quite sure exactly what that's for, but that's something to do with the feedback for, well, OVP stands for over voltage protection, so something to do with over voltage feedback. So in order to regulate the output, on here we've got a feedback input, and it shows the second half of the one half of an optical isolator there. Now I think that must be, was wondering actually what this little joker here was, but that's obviously an optical isolator, and on one side it's got an LED, and on the other side it's got a phototransistor. So in between there's an insulating layer, so you've got the insulated between there and there. So if we have an LED somewhere on the secondary here, that will give you, probably it's arranged so that it only lights up once the voltage gets up to what's required. When it lights up, then it'll turn on this phototransistor and give you a feedback signal there. So this is the way that this chip can actually sense whether the output is at the right voltage or not. A lot of complicated circuitry in here, much more complicated than most of the chips we've looked at before. We've got an on-chip thermal shutdown there, got a load of fault logic there, which has got various possible fault conditions coming in. We've got an oscillator, a green mode oscillator or something. That's something to do with maintaining, minimizing the current. And SS, forget what that stands for. And there's a status, which is presumably an output, which will give the status of it as to whether it's in a fault condition. So I think probably the only remaining thing that we can do, if I can find it, I put it somewhere else. I've got so many bits of disassembled lamps here. I think it's in here somewhere, or did I take it out? There it is. Okay. Right, so the one remaining thing that I'm still trying to ascertain is what these two little bronze coloured chips there are. And I'll make one or two inquiries and see what we can find out. But my suspicion is possibly the LEDs in these chips, in these packages, have failed, which is probably what's caused it to fail. Because the rest of it, it looks as though it's a very sophisticated lamp, much more sophisticated than any that we've seen before. And as I said before, all this metalwork, they've obviously thought quite a lot about dissipating the heat. Luminous lighting, it says. I might look them up and see what it says. It doesn't give the lumens output, but it's obviously meant to be, it's not just a cheap Chinese device. Right, so I shall see what I can find out about those little jokers there. And if I can find anything, I'll come back and we'll finish off this lamp before going on to the next one. Well, it took me a little while to work out what these two extra little devices here were. The obvious thought was that they were red LEDs for colour balancing, but then you would have thought if you wanted to colour balance accurately, just throw in a couple of extra red LEDs wouldn't really be the scientific way to do it. So what else could they be? Well, I wondered about some sort of temperature monitoring or temperature compensation. Well, or light monitoring or compensation, but then if it was any kind of monitoring, you'd need more than just these two connections to it. So could just be some sort of temperature compensation, because the forward voltage of an LED will decrease slightly as it increases in temperature. So you might just want some kind of temperature compensation. But even so, I couldn't quite see it. So there's an electronics forum that I use occasionally. It's quite useful on the All About Circuits website, allaboutscircuits.com, and the electronics forums there are quite useful, and quite knowledgeable people inhabit them. So I posted a question and asked if anybody could work out what they were. I got a few replies, but nothing very helpful really. But somebody immediately suggested, well, I need to scrape away the protective covering from this, just to see how the devices are connected up. And when I did so, I found that they were all in fact connected in a series. Well, in a sense that compounded the problem, because if these are red LEDs, then they're all in series and they will take exactly the same current as the other ones. So no chance of actually adjusting it finally. So again, it just compounded the problem really. So having scraped away some of this covering, I in fact damaged one or two of these phosphorescent domes. So I thought, well, let me see if I can just lift one of these domes off. And I lifted this one off here, and it came off and left the chip behind. So I thought I'd test these. Well, in fact, before I actually did that, having got the surface off, I could then actually test these with the test meter and see if I could get any of these to light up. See which of the LEDs, if any, was still working. So I connected onto there. That, it would seem, would go onto the bond wire of this device, and if I touch that on there, it lights up. And likewise the next one, that lit up as well. But neither of these two on this side, nor either of those devices did anything at all. In fact, if I tried measuring the resistance across there, across either of those, it showed up as open circuit. So whatever it was, it had failed, but that still didn't resolve whether it was some sort of monitoring or correction device. I suppose it could have been some sort of protection device if it had failed open circuit because it had got overheated or something like that, but it didn't sound very plausible to me. So as I say, I took the phosphor coating off this one and it left the chip behind. Now I think the chip does get damaged as you try and touch the pin on the surface, so we might not be able to do this, but if I get my other glasses on, we might just be able to get that one to light up. Now I'll need positive on the substrate, just there, and if I touch the negative on the surface, can I, yes, just lit up there for a second. Did you see? Yes, that's it. So that lights up quite nice blue. I think you could just see that. So the actual LED chip is still okay, but it must be either the bond of the chip to the base or the bond wire which has failed. He's working in quite high temperature, so perhaps that's not terribly surprising, though it should be designed obviously to cope with that. Okay, so having managed to show that that was still working, I tried the same trick on a next one. In fact, I tried pulling the transparent dome off this, but in fact the chip came away from the base and was left in the dome. So I then placed that on the desk in front of me and touched the negative on the the positive on the base of the actual LED die and touched the negative on the top, and it actually then lit up red, but it was upside down, so I couldn't quite see what was happening. One reason I was reluctant to say that these were definitely LEDs was because the die was obviously much bigger than a typical LED. Very often the actual chips, for instance, in these things, the actual chip in here, you might even be able to see it in this one. The actual LED chip, if I can get it to focus. There are actually 3 in there, and they're so small you can't really see them. So a red LED that big didn't seem very plausible. Let me get that back. Right, there we are. So I had this die actually on the desk in front of me and managed to get it to light up, but it was upside down, so I couldn't quite see what was happening. So how to make contact with the base, with the back of this die, so that I could actually touch something on the top and actually see it light up. Well, I spent a little while thinking about that. Eventually I hit on the idea of attaching it to a piece of copper foil. Here it is. I've got this copper foil. In fact, I think this it's adhesive on the back. This is used very often for screening purposes. I think people with electric guitars use this stuff for some reason. I'm not quite sure why. So I've got some of this at any rate. And I put a nice good blob of solder onto here, and while it was still molten, keeping it molten with a soldering iron on the corner, I pressed the die onto it, and at the second attempt that actually worked. I could then make contact with that and get it to light up. I don't know whether it's going to oblige us by doing that. Now we can actually try, see if it'll do anything for us. So if I connect the red to the copper foil, I think I'm going to need my eye loop to do this, because it's very, very tiny, and I hope I don't get my head completely in the way. Let's see if I can do that. If I then touch, yes. Did you see that? And it did actually light up bright red. And in fact, I did actually manage to get a close-up photo of that. If you try immediately just like that, I don't know, probably on the video it would have just completely overexposed. So I put a fairly large resistor in series so that it just glowed just sufficient to show the whole die lighting up. And here's the photo that I took. Here it is. You can see the whole die lighting up when I managed to touch the pin on the surface. So that was the explanation of that. Quite interesting. Why they did it that way is slightly puzzling. I don't know why they did it, but I think actually reading a little bit, if you look up LEDs on Wikipedia, there's quite a good section on white LEDs, and it seems there's been a lot of development in terms of the phosphor compositions in order to get a good colour balance. So probably, as I say, I think this was the first LED lamp that I ever had. So obviously things have moved on quite a lot from there, and they've got better phosphors that they can use these days to get a better white light. So I think that wraps up this. Just one other thing. This has got a lot of heat sinking, but even so, this device, this lamp, it said, is that in focus? I don't know. It says 6 watts. Well, 6 watts with just 6 of these LEDs means that you've got a watt for each of these, which means they're going to run pretty hot. Very often with this sort of thing, each individual chip is probably running quite a lot cooler than that. So even though we have got quite a lot of heat sinking, this is actually getting rid of that heat is probably quite a thermal challenge. So that's maybe why it actually failed. I forget whether I said I probably had that in use for 5 or 6, maybe even 7 years before it failed, but it did eventually. I think that just about wraps up this one. So I'll come back. I've got a couple more to do, 2 or 3 more to do. I've got this. Quite looking forward to seeing what we can do with this, and 1 or 2 others. Actually, one other thing that I'll just show you while I'm here. I don't know whether you know, but if you get a UV torch and shine it on here, you can get it to light up. I've got this, we're still on, zoomed in, I think. Let's zoom it out again. So I've got this UV torch, and if you shine it on one of these, it very often lights up. This demonstrates that these things have got different phosphors. So if we do that one, that doesn't seem to light up nearly so well. But on the other hand, this one, that's lighting up pretty well. On the other hand, some of them seem to respond to blue light better. And if I get my LED tester, and I've got a blue LED in it. Here we are, the blue LED. Let's see what that does to any of them. That seems to light that up fairly well. And this one, I think that's probably lighting that up better than the ultraviolet, but unless I take it in really close, which causes it to be horribly overexposed, it doesn't seem to show up terribly well. But this one, there again, that doesn't light up nearly as much as it did with the UV torch. So that just demonstrates there are actually different kinds of phosphor formulation that they use in these, and evidently since this one was produced things have moved on somewhat. Okay, so we'll come back another time when I've got a bit more to show you, and well, I'm wondering how I'm going to get into this. I think I might just have to put it in something protective and hit it with a hammer and break the glass. Don't like doing that, but I don't see another way of doing it. So if I haven't bled to death after that, I'll show you what I can find when I get inside this. Okay, well, thanks for watching if you have, and I'll see you another time. No, I won't. You'll see me another time, or my hands at any rate. Right.